Hello. Does this work? Okay, great. All right. Good morning, everyone. I'm Sajin, and today I'm going to be presenting ConsenSGX, Scaling Anonymous Communication Networks with Trusted Execution Environments. And this is work by myself and my supervisor, Ian Goldberg, from the University of Waterloo. All right, so let's get into it. As we all know, I'm going to use actually a toy example of the Tor network to illustrate the problem that this work tries to solve. So as we all know, in order to connect anonymously through the Tor network to a web server, a client needs to choose 3 random relays in this Tor network, as Hans pointed out. And so in order to do this, the client needs to have absolute autonomy in the selection of these random relays, lest they be susceptible to a branch of attacks called as epistemic attacks. And to facilitate this, Tor today uses a special set of relays called as directory authorities in order to facilitate a global view of this network to this client. And specifically how this works is that at the start of every epoch, which is a 1-hour window, all relays in this network send a self-signed blob of text called as relay descriptors to these directory authorities. These relay descriptors contain all of the parameters of this relay, such as their IP addresses, their cryptographic keys, their ports, and other parameters required by the client to create a connection through them. And at the end of this, the directory authorities perform a consensus protocol amongst themselves to produce a document called as the network consensus. This network consensus is in effect a global view of this network. And it looks something like this. I'm surprised the slides just keep going downwards, but okay. The network consensus looks something like this, which has all of the global parameters at the start, followed by all of the individual relay descriptors that the directory authorities saw in this epoch. Finally, the directory authorities all sign over this document, and this document is published in the Tor network. So before the client can actually make any circuits, it has to get a copy of this network consensus. Sorry? Yeah, I think that's probably better. All right. So before the client can actually make circuits in this network, it needs to get a copy of this network consensus. And in order to do this, either the directory authorities publish these documents, or they're also served by special relays in this network called as directory caches. So once the client actually obtains a copy, it can continue to make circuits in this network. But the thing to notice here is that this network consensus document scales linearly in size with the number of relays in this network. So as more clients join this network, you have more of these network consensus documents that need to be sent across this network. And so this induces a total bandwidth overhead in simply distributing the global view of this network. And this scales linearly with the number of relays in the network, as well as with the number of clients in this network, which is bad. Definitely, the latter part is inevitable in the sense that some amount of bandwidth needs to be sent to each client so that they can see some portions of this network to make circuits through. But we can definitely do better in the former part of it. And that's exactly what this work tries to achieve. So there's been a lot of previous work in this space. And broadly, the work can be classified into 2 different buckets, peer-to-peer models as well as client-server models. But all of the known peer-to-peer models have been shown susceptible to one form of attack or the other, and I won't be speaking about them in this talk. But in our paper, we do reflect on different models and the different attack vectors that open up to these particular models. As for client-server models, there's just one that we know of, which is PeerTor. PeerTor proposed using private information retrieval techniques towards solving this problem. So the idea is that the client can use PIR techniques to download a subset of relays within a network consensus, and then use those to build circuits for that epoch. And in this very sense, they investigate 2 different types of PIR protocols: information theoretic PIR, IDPIR, which are efficient in practice, but they eventually dismiss it because of the non-colluding server assumptions, which are hard to realize in practice. They also investigate computational PIR, for which they particularly use a fast PIR protocol by Aguilar-Melchior and Gaborit, but this protocol now is broken because of the non-standard lattice assumptions that they used. And so we evaluate our work against PeerTor as well with a more state-of-the-art PIR scheme. Before I can speak about ConsenSGX, I'm going to speak a bit about the background required for this, or specifically the trusted execution environments that we speak of. Or in this talk, I'm going to limit myself to Intel SGX, which is also the trusted execution environment we used for our proof of concept implementation. So SGX, our software guard extensions, are a set of extensions to the x86 instruction set, and are available on all Intel processors from the 5th generation onwards. These processors are fused with secret keys at manufacture time. And this in turn allows the processor to set aside a portion of the DRAM as PRM, or processor reserved memory. And again, this in turn allows the CPU to instantiate secure virtual containers called as enclaves. These virtual containers can be loaded with programs that give you confidentiality, integrity, and freshness guarantees based off these cryptographic keys from the CPU. And finally, it also has this protocol called as remote attestation, which allows the user to verify that the program that you're loading into this enclave and running on is in fact running in a trusted secure hardware and is in fact running the particular program that you wanted it to. The final last piece of background that I have to speak about is ORAMs, which is what we use for ConsenSGX. So ORAMs or oblivious RAMs are a cryptographic primitive which allow users to access memory on a remote server without leaking anything by the access patterns. So ORAMs have been around in the theoretical realms for about 2 decades, but barely used in practice because of the fact that they induce extreme overheads. Typically, they involve significant client-side computations, as well as large client-side memory, or small client-side memory, but multiple network round trips for a single access. But with the advent of the trusted execution environments like SGX that I spoke of earlier, we're seeing more practical constructions for them. Specifically, these constructions have been called as doubly oblivious ORAMs, and there are several such as zero trace, obliviate, or oblix. In all of these constructions, the ORAM controller logic and state itself is moved into an enclave on the server side, and thus allowing users to just interact with this directly. But as you move this to the server side into a secure container, you have to rewrite this in an oblivious fashion so that you're not susceptible to side channel attacks that are known against these trusted execution environments. And finally, the interesting cool part about this is that it also trivially enables a single client ORAM protocol to support multi-clients. Finally, coming down to ConsenSGX, the high-level idea of our project was to use trusted execution environment-aided ORAMs to retrieve a subset of the relay descriptors of a consensus obliviously so that the client can build circuits while not opening up themselves to epistemic attacks. And our solution is efficient in that even though it introduces computational overheads, these are very small in the order of a few milliseconds and are broadly dwarfed by network transmission round trip times. It's scalable in that even as the number of relays continue to scale drastically, the solution is still practically feasible as we show in our evaluations later on. It's incrementally deployable as it simply adds on as another consensus mechanism that Tor can choose to support. But deploying an ORAM or PIR scheme has several challenges in practice. It implies ORAMs or PIR schemes typically access files or memory by the notion of indices. And relay descriptors within a network consensus does not lend itself directly to a notion of an index. Additionally, these schemes also use static block sizes, but relay descriptors are of varying sizes, and so selecting the optimal block size for these schemes become a hard problem. Finally, since we also have to provide authenticity or integrity guarantees at a fine granular level of each relay descriptor, this implies all the directory authorities have to now sign each descriptor individually, and so we end up adding more bandwidth because of the multiple signatures that get attached to each relay descriptor. So in a paper, we also speak about techniques to compress the bandwidth overheads that come from this. And also we speak about how to bootstrap this scheme. But in the interest of time, I'm not going to speak about all of this. I'll speak a bit about the indexing part of it and then continue on with other parts of ConsenSGX. So as I mentioned, we need an indexing scheme so as to actually retrieve relay descriptors in this. Unfortunately for us, as we've all just noticed before as well, in Tor, the relays that are selected for circuits are actually done using a bandwidth-weighted mechanism. That is to say that the higher bandwidth these relays have, the more likely they are to be selected for being used as a relay in the circuit. And so we propose using the same bandwidth ordering towards indexing the schemes. So specifically what we imply is that the directory authorities order the relays in a network consensus by their decreasing bandwidth. And so to this end, we actually plotted the bandwidth descriptors in the network consensuses from September 2018. And it turns out that the bandwidth ordering follows an exponential curve. And if you plot that on a log linear plot of relay bandwidth versus relay number, you get a linear line. And this can be easily approximated by the blue line as we show in that graph. And so this line can then be presented by just the slope and intercept of this line. And so as you publish this, the clients can in fact generate this line on their client side and sample based on their bandwidths again. Now our proposal also introduces 2 new types of consensus documents, which what we do for that is we consider the old network consensus document as is, and we partition that into 2 pieces. The first one contains all of the global network parameters. So it has the global network parameters from the consensus, and also the number of relays, the bandwidth distribution parameters that we spoke of in the slide before, and finally, this entire document is signed by the directory authorities itself. And we call this as params ConsenSGX, but it's essentially a parameter file which every client in the network still has to download. But the important part about this document is that this is independent of the number of relays in this network and is of small size, and typically around the order of 4 kilobytes or lesser, which is much smaller than the network consensus, which is around the size of 2 megabytes today. The other the consensus document required actually contains all of the relay descriptors itself, but as we mentioned before, since clients would now download relay descriptors at an individual granularity, they have to be signed and have an associated index to them as well. And we call this the network ConsenSGX. But this document itself is not downloaded by the clients. These are meant to be distributed to the directory caches that would serve ConsenSGX. So the clients never have to pay the bandwidth for actually downloading them. And finally, we'll show how the request and response flow looks like in this architecture. So assuming that you do have a directory cache that has support for the trusted execution environment and is currently running an ORM controller with an ephemeral asymmetric key pair that's published in a former network consensus, once it gets the network ConsenSGX for the current network, the directory cache can then continue to load up the ORM backends or the ORM trees for these from this network consensus document. And once this has been set up, a client who has the params file for this particular epoch can sample indices from the distribution that we spoke of earlier, and these indexes then just become the requests for this particular epoch. And so this client can generate the set of indexes, which are the requests, and encrypt it with an ephemeral symmetric key. The ephemeral symmetric key itself can be encrypted with the public key of the ORM controller. And these requests can then be sent forth to the directory cache through the one-hop circuit for directory lookups. The controller that receives this request can in fact decrypt the ephemeral key, decrypt the set of requests, and perform the ORM accesses for this at the back end. Once the ORM responses are accrued, the ORM controller can encrypt it under the same ephemeral symmetric key and send it back to this client, completing the entire flow where only the client knows what indices that it requested for and correspondingly receive the relay descriptors for that. All right, and finally to speak a bit about our evaluation, we evaluated against CPIR, specifically the XPIR library for this, and ITPIR we evaluated against the Chor scheme, and also the current Tor microdescriptor consensus model and the diff variant of the microdescriptor consensus model. In our evaluations, we introduced the notion of a parameter called as B, which is the batch size or the number of relay descriptors a client would fetch at a time, as opposed to fetching individual relay descriptors required for each circuit construction. And so the graphs that we'll see today will have B for 50, as a value of 50, which implies 50 relay descriptors at a time. So this graph shows an end-to-end time evaluation, which we extrapolate based on the assumption that the Tor guard nodes have a bandwidth of 4 Mbps. And as you can see here, the CPIR scheme is clearly impractical just because it costs about thousands to 10,000s of seconds in practice. And this is mainly because of the underlying FHE scheme, which makes it extremely heavyweight and hard to use in practice. As you can see, there are lines for the Tor microdescriptor consensus and the diff of the Tor microdescriptor consensus. We extrapolate these lines from the average of the consensus sizes from September 2018. And similarly for the diff, it's extrapolated from the 1-hour diffs of these consensus from September 2018 as well. We assume that as the number of relays increase or decrease, the sizes scale linearly. And it turns out that the ITPR scheme is actually faster than the current consensus mechanism of Tor, but as Tor pointed out as well, this has non-colluding server assumptions which are hard to realize in practice, and so we don't support this idea as well. But what you can see here is that ConsenSGX in fact scales really well even as the number of relays continue to increase drastically. And this is where we are currently at in terms of the number of relays from Tor. So it's around 6,300. And what you'll notice here is that our solution is even pluggable into the Tor network today, and it'll give you bandwidth optimizations. But you might notice here that the diff version actually does seem to perform better, but the important thing to note here about that is that the diff variant only works if a client is online. So the moment a client goes offline for more than 5 hours, you default back into the Tor microdescriptor consensus model, and the diff version no longer holds for you. Finally, we also realized that it might be hard to expect overnight Tor to have suddenly support for trusted execution environments, and so evaluate what fraction of the relays should actually have support for such trusted execution environments for this to work. And so it turns out that even if the number of relays were to scale drastically, as long as 2% of the entire network has support for this, we can in fact serve all clients within an epoch. And here we assume that the number of clients to relays scales linearly, or stays the same as the number of relays increase. And the other important part here is that this graph only assumes that each relay that does in fact have trusted execution environment provides one core towards this purpose. So if you were to introduce the notion of parallelism and further cores thrown at it to serve this purpose, we could in fact have lesser trusted execution environment requiring relays. Finally, again, we're at this mark here. So today, if you were to use this, this consists of around 1.5% relays of the network. The other interesting part about this graph is that the average bandwidth required in this scheme. So for these relays that in fact do have trusted execution environments, the average bandwidth requirement is 0.812 Mbps. So we point out in our paper as well that this actually creates a new opportunity for Tor to use some of its low network bandwidth relays towards serving directory lookups, as they have a lesser chance of anyway performing in, as they have a lesser chance of being a part of circuits anyway because of the fact that circuits relays are chosen by bandwidth sampling. And finally, since I've come to the end of my talk, just to reiterate over all the parts that I've spoken about, distributing the global view of anonymous communication networks is not as scalable as the network grows. And our proposal defends clients against epistemic attacks while not enforcing clients to maintain a global view of the network. And the evaluations of ConsenSGX show that they're actually practically deployable and scales even as the network grows. And our paper and source code for reproducing experiments are available at the CRISP website. Thank you. And with that, I'll take questions.